Welcome to our 6th lesson on chemical equilibrium. We're going to be looking at the industrial processes and how the chemical equilibrium plays a role there. Now we're going to be looking at 3 industrial processes. We're briefly going to mention them and where this chemical equilibrium does play a role. But the reactions as such and the products of these processes you will still do in detail in your very last section, which will be on chemistry in grade 12. So just to briefly touch on it, in your Haber process we will be manufacturing ammonia, and ammonia is known as NH3. In our Oswald process we will be manufacturing nitric acid, and nitric acid is known as HNO3. And in the contact process we will be looking at the production of H2SO4, which is sulfuric acid. Now in each one of these processes there's going to be different steps before we're going to get to the final product. But we will only be looking at maybe 1 or 2 of these steps and how the chemical equilibrium plays a role in those steps. So we will not be looking at the whole process. As said, that is something that you'll discuss in your very last grade 12 lesson. Now the whole idea during these processes is to ensure that we will end up with a high yield of product. That means a great amount of either ammonia or nitric acid or sulfuric acid. But that means we'll need to change some conditions during those reactions in order to ensure that the forward reaction is favored in most cases, seeing that our forward reaction is going to produce our products. But we will need to take into consideration all the factors that will affect the equilibrium, as well as the factors that's going to affect the rate of the reaction. Now in our Haber process, as said, we would want to produce ammonia. Now the one specific reaction we will be looking at is the only one that is found in the Haber process, and that is where the NH3 is in the products. Now if we want to end up with more NH3, we can go and look at pressure in this case. So seeing that everything is in the gas phase, that's how come pressure is one of our options. But now the question is, do we need to increase or decrease the pressure in order to favor the forward reaction? Now if we go and look at the forward reaction, that means we'll end up on the product side with 2 particles and we'll start with 4. So that means if we want the forward reaction to be favored, that means less gas particles to be produced, then we need to make sure that we increase the pressure. Because as we increase the pressure, the system will end up decreasing the pressure, and it will do so by favoring the side with less particles. Let's go and look at another way. A key point that we can still look at is our delta H value. Note that it has got in this case a negative value. That means the forward reaction is thus going to be an exothermic reaction. Now we want the forward reaction to be favored because we want to produce more NH3. But in order to let the system favor the forward reaction, which is exothermic, which means it wants to increase the temperature, we would need to go and decrease the temperature. So if we go and decrease the temperature, then the system would like to increase the temperature, and it would do so by favoring the exothermic reaction, which is then the forward reaction. But now there's a catch. If the temperature is decreased by us, we need to take into consideration those 5 factors that affected the rate of the reaction. That means how fast the reaction occurs. Now, in this case, a decrease in temperature will slow down the rate of the reaction. And that would mean it will take way too long for the ammonia to form. We need this ammonia to be formed faster because of our production that we need to take into consideration. So therefore, a decrease in temperature is not an option. Even though it might favor the forward reaction, it's going to take too long to form the products. So therefore they'll need to go and find what we call an optimum temperature, which in this case is around about 400 degrees Celsius, which will still more likely favor a bit of the forward reaction, but not slow down the reaction too much that it takes too long for the product to form. Now 2 of the process steps in the Oswald process actually also have a delta H of less than 0. which means that if we would like to favor the forward reaction, a decrease in temperature would also not help, because a decrease in temperature would actually, although favoring the forward reaction, make the reaction too slow, and then it will produce too little of my product in a certain amount of time. Now, you were to take note in this specific reaction, one of the steps forms the nitrogen monoxide, and the next step uses this nitrogen monoxide again in order to continue forming more of the products to end up with our nitric acid, which forms in the Oswald process. Now, one way in which they are trying to make sure that the temperature stays low but the forward reaction is still favored and that it happens fast enough is to take this nitrogen monoxide that is now formed in our previous reaction and then cool it down, the gas, before they use it in our second reaction. And this cooled nitrogen monoxide will then in this case favor the forward reaction, and it would not influence the rest of the reaction's temperatures too much, which means it will still happen at a fairly fast rate. Now, for your contact process where we form our sulfuric acid at the end, one of its steps also has a delta H of less than 0. Which means that if we want to favor the forward reaction, we can though not go and decrease the temperature, because that would make the reaction too slow. So it's also going to operate at around about an optimum temperature of 400 degrees Celsius, which is not too hot so that it doesn't favor the reverse reaction, but it's not too low so that it is not going to slow down the reaction. Now, just like in the case where we looked at our Haber process, we can go and look at this case at pressure as well, because each one of our reactants and products is in the gas phase. Now, if we look at our reactant side, there's 3 gas particles, and at our product side there's 2 gas particles. So if I want to go and favor the forward reaction, I can just go and increase the pressure, because then the system would like to end up decreasing the pressure, favoring the side with less gas particles, which in this case is the forward reaction. One would though need to take into consideration that when you use pressure, whether it's now an increase or decrease, it's going to use a lot of electricity to actually make this apparatus function. So it has a bit of a financial drawback when you look at your yielding of the product at the end of the day.